Good evening. My name is Koichi Wakatta of Japan Aerospace Exploration Agency. Currently serving, I'm an astronaut of Jaxa and currently serving as the Vice President for Human Space Flight and Exploration. First, I would like to express my sincere gratitude to Mr. Blasberger for inviting me to this wonderful city. It's my first time to be in Israel. I flew over Israel many times on board the space station, but it looked really beautiful from the space station, and actually it is beautiful. And I just arrived yesterday at 7 a.m., and I'm just honored to be here. I had such a fond memory of working and training with Ilan Lamon when I was stationed in Houston, Texas at the NASA Astronaut Office for more than 20 years. And this photograph that you're seeing here is a photograph of your familiar area of Sinai Peninsula, and it was taken by my colleague, Jaxa astronaut Takuya Onishi in 2016. Today, I would like to talk about with this theme of why in space. So I'll give my presentation in those three main parts, uniqueness. To answer this question of why space, I'd like to introduce, the uniqueness of space first, and then how to make the best or good use of that uniqueness. And our activities in space is the next, and then finally I'd like to talk about space for education. Of course, in front of the great educators, here I'm privileged to talk about the space for education. So last year, you mentioned, you saw Charlie Bolden's remarks today, former NASA administrator, but last year marked the 50th anniversary of Apollo lunar landing, Apollo 11 mission. And to date, there were more than 565 people who have flown in space. And when I saw the Apollo 11 landing at the age of 5, I still remember that I had a strong desire to fly in space. And but at the age of 5, there was no Japanese astronaut, there was no rocket, produced in Japan. I thought it was impossible to fly in space. I simply thought that's just some dream beyond my reach. And but because of the strong desire that I had to fly in space, I'm here with you. And when Neil Armstrong, Buzz Aldrin, and Michael Collins were executing this very important mission for humanity 50 years ago, this is what I was doing. And I don't know, this is Ultra 7. I was 5 years old in a Japanese shrine, and I was very happy to take picture of with Ultra 7, my hero. And the drawing that you see on the left side are my favorite things. Upper side, actually my wonderful teachers allowed me to write those drawings on the back side of a quiz of arithmetic. And this was when I was 6 years old, but I was drawing the Apollo orbit on the upper side, and the lower side was my favorite airplanes. And that was the strong impact that I had when I saw the Apollo 11 landing. And thanks to the international collaboration, I was able to join the NASA astronaut training like Ilan Lamon did in Houston, Texas. The red one, the circled one, is me. I was the youngest in the class of 1992. 24 people in the class, 19 Americans, 2 Europeans, 1 from Italy, 1 from France, and then 2 from Canada and 1 from Japan. And I was the youngest in the class. The youngest person in the class usually receive a pacifier that says remove before flight. And I removed that before I flew in space. And thanks to the great training that I received at NASA, I was able to fly on the space shuttle, Soyuz, and the International Space Station. I flew a total of 4 flights, and I spent in zero gravity for 347 days or so. And as I mentioned, I had such a fond memory of working with Ilan in Houston when I was stationed there. And the most memorable training that I had with Ilan was what's called the NOLS training. It's expeditionary behavior training in the mountains of Wyoming State in the United States. In this training, NOLS training, Ilan demonstrated his excellent skills in leadership, followership, self-care, team building, teamwork. And what was really surprising to me was that he's a very energy efficient guy. He can continue to climb and go in the mountains with only coffee for many hours. I had to eat a lot. So I thought, wow, this Israeli guy is a very energy efficient guy, and it was very impressive. And it was my honor to work with him. And so as one of the many people around the world engaged in the human space exploration, I believe it is our duty to continue the legacy of Ilan and STS-107 crew by always remembering the hard lessons that we learned in order to make the safety of space flight. So let's talk about the uniqueness of space, one of the three things that I mentioned in the beginning. Space has many uniqueness, such as these four things. For example, not affected. Space is not affected by terrestrial conditions. The next one is microgravity. And this is a unique environment in the space. And also, space has a hint for the origin of the solar systems and space, of course. And then international collaboration. Space is a place for conducting international cooperative projects. So how we can make the most of space missions, space uniqueness, is in how what we can do there is the topic that I would like to talk next. So firstly, we can utilize the first quality of space, which is not affected by terrestrial conditions, is to monitor Earth atmosphere or Earth environment using satellites. For example, Japanese satellite, the GOSAT, was launched in 2009, GOSAT-1 to the left of the picture. And this continues to observe greenhouse gases. GOSAT-2 on the right side was launched in 2018. And so therefore, there are two Japanese satellites now orbiting around the globe to observe the greenhouse gases. As the World Meteorological Organization of the United Nations published at the end of 2019, the increase in global greenhouse gas emissions still continues. Space-based observations by GOSAT series give the same result. So this is the global CO2 concentration has increased by 2.4 parts per million over the past year from September 2018 to September 2019. The GOSAT series has focused its observation on the major cities, which are set to emit the majority of CO2. Also, the GOSAT series are able to observe the lower and upper layers of troposphere. Concentration in the lower layer directly reflect the effect of emission in cities. Therefore, the observation data of the GOSAT series can be used to reduce emission, and efforts are underway towards this goal. Under the framework of Paris Agreement, each country that is party to the agreement must report its own country's greenhouse gas emissions. So-called inventory, this is. So GOSAT series data are obtained from the entire globe, and it is expected to provide a scientific basis to verify the accuracy of inventories reported by each country. The United Nations IPCC, Intergovernmental Panel on Climate Change, has also newly incorporated satellite data as a method for verifying inventory reports into guidelines, which present calculation methods for getting an accurate understanding of amount of greenhouse gas inventory. Another example of making a good use of the uniqueness of space is monitoring disasters. The International Disaster Charter utilizes 61 satellites from the countries around the world and has assisted in disaster monitoring in 126 countries. When the charter is activated, satellite data for disaster areas can be obtained in hours or 2 days. The transmission of images is continuous through the period the charter is active for, and it provides the disaster relief organizations valuable information on disasters that could not be obtained from the ground sources. And even when not participating in disaster charter, as shown here, a country and time can be specified to search through when and where various kinds of disaster occurred. And for example, in Israel, as you can see here, there was a wildfire in November 2016. Natural disasters are a global scale issue, and properly understanding them facilitates the emergency responses and the relief work that follow. So next, I would like to introduce activities that utilize the uniqueness of microgravity. When we have headaches or fevers, of course we take medications, but do you know why we take medicines to relieve headaches and reduces fevers? It turns out that the role of most medicines is to bind to proteins in the body and molecule and modulate how these proteins act. In other words, if we can gain a deep understanding of the action of the disease-causing proteins and how they exert their effects, we can design the drugs to control diseases. Knowing the detailed structure of proteins allow their function to be predicted, and it will enable the design of compounds to facilitate or inhibit those functions. So investigating the structure of proteins causing diseases can be considered as indispensable in developing new designs. Protein molecules are very small, 10 nanometers or less in size, so it is very difficult to understand the structure using just simple microscopes. That's why we crystallized molecules, protein molecules. In a crystal, the protein molecules line up in a regular manner. And by analyzing the structure of crystals with X-rays, we can visualize the structure of protein molecules. On the Earth, it is very difficult. It's not easy to produce high-quality protein crystals because the disorder of the gravity disorder of arrangement of the proteins due to gravity is happening. So in space, in microgravity, we can produce high-quality protein crystals that could not be made on the Earth, on the ground. Therefore, utilizing the microgravity in space are facilitating development of technologies such as new drug design. Next, I would like to introduce some activities for elucidating the origin and the evolution of the solar system. You may have seen this picture of asteroid explorer Hayabusa 2. The Hayabusa 2 explorer of asteroid is a successor of Hayabusa 1, which demonstrated several new technologies and returned to the Earth in 2010. And not only did it establish new navigation methods of using ion engines, but the Hayabusa 1 spacecraft also brought back samples from the asteroid Itokawa. This is to help elucidate the origin of the solar system. By leveraging the experience of they acquired from the Hayabusa 1 mission, the follow-on mission, Hayabusa 2, targeted a C-type asteroid. This is called the Ryugu asteroid, and this is to study the origin and evolution of the solar system as well as the materials for life. Hayabusa 2 has departed the asteroid Ryugu in November, a couple months ago, and is scheduled to return to the Earth at the end of this year. And I would like to talk about international cooperation in space. It has been over 20 years since the start of the on-orbit assembly of the International Space Station. 15 countries have been working together in its planning and also execution of the utilization plans. This year marks the 20th continuous human presence, 20th year of continuous presence on orbit since the year 2000. So anybody who is older than 20 years old have never been on the Earth when there was no astronauts flying in space. So as well as being an excellent on-orbit laboratory for advancing science and technology utilizing the space environment, the International Space Station is a symbol of international cooperation and peace. In the future, we will further expand human frontier in space, and many spacefaring nations are making efforts into space exploration with a focus on the moon and Mars. Israel, of course, is one of the countries sending a lander to the moon, and I understand there's a future attempt to proceed on the exploration effort. Discussions have begun into the activities on the moon, such as base building on the surface of the moon, and these activities will also include participation of industry partners and international collaboration. We are through a mutual cooperation as citizens of the Earth, facilitating the participation of many players with the goal of expanding the range of our activities in space. Next, I would like to introduce these three efforts that are being made in space education. And this is to utilize the Japanese experiment module Kibo on the International Space Station. I will give you some of the examples. This first one for the space education example is a robotic programming challenge. It's called the Kibot Robot Programming Challenge. This is a contest planned for educational goals to solve various problems using actual robotic drones on the International Space Station. You can see those two drones. One on the left is called Astro B of NASA, and the Intball robot, that's a Jaxa drone in the space station. So this program is a joint effort between NASA and Jaxa, and the participants create their own own programs to automatically control the NASA Astro B drone. And using the marking of the inside of the space station as a visual aid, we can have Astro B travel to a goal, stopping it at an appropriate location. And this is how we do the demonstration and competition. So the participants will compete on the time and accuracy of the moment, of the movement. So let's take a look at the video of this attempt of this Astro B and Intball robot programming challenge. The right side shows the Astro B's motion. As you can see, Astro B moving to the right. And the left view, two views show the video seen from the Astro B. And you can see that it makes appropriate movements, and it aims, looking at the target that is shown in this left side view. And for space for education, I can give you another example, which is the capacity building, capacity development through small satellite deployment. At Jaxa, we are promoting capacity building through developing small and cube satellites in the university in Japan, such as Kyushu Institute of Technology or the University of Tokyo. And we are also assisting them to deploy the satellites from the Japanese Kibo module. The Kibo module that you can see on the right side picture on board the space station is the only module on board the space station that has an integrated robotic and airlock capability to deploy small satellites. So to date, we have already deployed more than 240 CubeSats from the Kibo module. And these satellites include first satellites from countries like Kenya, the Philippines, Costa Rica, Ghana, and many other countries. So we are helping build their technology in space for those startup countries in terms of space exploration. So it's my honor to, and I feel very privileged to be able to talk in front of you, the educators, and each one of you here present, plays an important, significant role in educating the next generation to move humanity forward in exploring the universe and exploring the new frontiers in space. It is our responsibility as spacefaring nations to further expand our human frontier in space beyond the low Earth orbit, and always with the spirit of harmony and partnership for the benefit of the entire humanity. And I'll be happy if today's presentation that I made has inspired you a little bit, and you will inspire the next generation to the new young generation. And I hope they will be interested in space exploration and broaden their perspectives. Thank you very much for listening. And I'll be happy to answer any questions that you might have. And Charlie Bolden said, ask hard questions. I'll be happy to take any hard questions if you have. Go ahead. Garbage? Good question. Of course, we have all kinds of garbage from experiments and food and clothing. Of course, we have to deal with. We have supply cargo vehicles like a SpaceX Dragon or Northrop Grumman Cygnus spacecraft, and also Japanese have. We have a cargo supply vehicle called HTV. So those cargo supply vehicles will carry the cargo. But we take out everything and we put this, garbage in that spacecraft. So the spacecraft carries the logistics, but it also used as a, a garbage ship. So when they undock from the space station, they carry those garbages with them, and during the atmospheric re-entry, will be destroyed. That's how we deal with the garbage. It's important to take out the unnecessary things because space station is very small, so we have to utilize the resources, but at the same time, we have to get rid of the unnecessary items. Good question. Go ahead. Okay. Of course, Charlie Bolden, he was a NASA administrator, but before that, he served on the 4 space shuttle missions, and I had a privilege to work with him in a simulator. So I learned a lot from great leaders like Charlie and many of my former commanders on my previous flights. So I was lucky to be able to learn from those great leaders in the past. And of course, each country, Japan is one of the 15 countries participating in International Space Station. So it is an important thing for Japan to represent the space station program by having a commander in the program. So I was just one of them. I was just lucky to be able to serve as a commander. But I was able to do that job because Japan is considered a reliable partner of the International Space Station. So I just happened to be at the right spot at the right time. I was just lucky, and I feel very lucky that I was able to learn from the great leaders of my predecessors in the space program. Thank you. Any other questions? Go ahead. Various what? What did you say last? What? Salt. Salt and pepper. For the crystal, the crystals that we kind of develop in space is for the protein.
Concentrations of various salts, various ionic strengths of the solution. That's the question. Did you try growing the crystals in different kinds of solutions, different molarity?
Right, different, yeah. So the mixtures of protein already is made when it's launched on a rocket. So what we do is we just keep them in a floating environment of microgravity. So we astronauts really do not change the composition of the protein crystals. So the ground people adjust the thickness of the protein crystallization so that we can make the best crystals in space. As I mentioned, we used protein crystallization for developing new diseases, right? New medicines against the diseases. So the constituents of the protein crystal is very important because unless you make the optimum solution, it's very difficult to have a high quality protein in zero gravity. So on the ground, they spend many hours to come up with the best solution in order for them to make the best crystallization. So there's a lot of experiments on the ground before they launch a protein crystal in space. All right, thank you. One last question, yes.
I read 2 years ago that Jaxa has launched an experiment to test the feasibility of space elevator. What is in your opinion, is the feasibility of this, and is there any other expected experiments in this area?
Of course, this is space elevator is a very fascinating concept and very exciting to see the development. And I'm hoping that it will happen in the very near future. But there are a lot of technical challenges that we have to overcome, especially this material strength, and it has to be light and strong. So the concept is very clear, and if we have that material ready to be used for that, it's still, I believe it takes a while before we make it a concrete program. And of course, there's a lot of technology challenges that they demonstrate the robotic missions to demonstrate this climbing up capabilities, but it's not to the geostationary synchronous orbit yet. So I think we have to spend more time for developing the light and strong materials. And other than that, I think I hope I can see that in the near future. It's hard to tell when. Are you working on that? Okay. Okay. Yeah, but I hope you can educate the new youngsters, to build the space elevators, and I'm looking forward to seeing that. So. Thank you very much.
Thank you, Mr. Wakata. Thank you. Thank you very much.